And welcome to the intermission. This is a picture of a hummingbird. It is cute. Just going to let things calm down for a while. Take a deep breath. And we're back from our intermission. Yes. So, where were we? Yes, we are going to deal with the cyclic permutation thing. So, given any positive integer m, such that chi-q of b2 of m is in our cycle omega, let z0 be b2 of m, and then let's define zk to be the image of z0 under k applications of the left shift operator. Next, we're going to let big theta be the set z of all the zk's. Letting n be the is equal to b2 of m, observe that, as we saw earlier, big theta has precisely lambda 2 of n distinct elements, because n is the the reason for this is that m's sequence of two adic digits might be a periodic sequence made up of, like, say, 0, 1, 0, 1 repeated 3 times, in which case our n here would be 0, 1, 0, 1, which is 10 in base 10. And then of course that has 4 digits, which is lambda 2 of 10. So because in other words, because I'll come up with terminology for this later. I call it the root. Because the shortest sequence, which when concatenated with itself infinitely many times generates the sequence of digits of z0, that shortest sequence is going to correspond to the digits of n. And that's going to have lambda 2 of n digits. And then since we're getting z0 by taking that sequence and concatenating it with itself infinitely many times, this means that as we apply the left shift to z, to go from the zk's, we just need to shift lambda 2 times before we've reset and we're back to where we started. So, suppose there is a y in z2, which is not in this set of cyclically permuted z's. And suppose that this y is sent by chi-q into our cycle. Then every element of our cycle is of the form h of some kth iterate of chi-q of y under by theorem 4, which now I have to go back because I didn't name them. Theorem 4 is by the first version of the correspondence principle. So by the first version of the correspondence principle, since this is a cycle, there's going to be some integer n prime such that the periodic part of y's two adic digits is generated by the two adic digits of n prime. Thus, n prime is to y as n is to z0. Moreover, letting a bold J prime be the string representing n prime, it must be that h bold J prime fixes this iterate for some k. Why? Because when we apply k, when we apply this sufficiently many, all we need to do is make it apply h a sufficiently large number of times such that the two adic digits of chi-q of y are then the same thing as are then generated by this the sequence of digits here. In particular, the two adic digits n and n prime cannot be cyclic permutations of one another, because the two adic digits of these numbers, they can't be cyclic permutations because we assumed that y was not in that set of permutations. But then this makes chi-q into a wrong value of h. In other words, the only possible bold j's which give the motions of z0, give the motions of chi-q of z0 under h. The only possible choices of j's are the j's that represent n or m, and which when we concatenate them infinitely many times, we get z0. There's probably a way to rephrase this more cleanly using just pure algebra, but this is how I prove it. So what we end up having here is that chi-q of y is a wrong value if chi-q of y was not a wrong value of h, then n prime's digits would be a cyclic permutation of n, so of n's digits. And so in other words, given any periodic point, there can only be one right value, and thus we cannot have two. So this then proves that if chi of z is in big omega if and only if z is in big theta. And then here m is the number we started the proof with, and m is the smallest positive integer such that b2 of n is no, this is wrong. This should be chi q of b2 of n is in omega. This then shows that the restriction of chi to big theta is a bijection from big theta to big omega, and thus they all have the same cardinalities. So, that out of the way, we've dealt with the periodic points. All that remains is to obtain the correspondence principle for divergent points. To do this, we need to just make a simple observation. And as I said, I was just like 2 weeks away from having to turn in my dissertation when I made this thought and realized what the implication was. So, we know that the periodic points of TQ in Z take away 0 are completely determined by the rational integer values that chi-q attains on rational 2 adic integers with infinitely many digits. So we have a correspondence between periodic points of TQ and, as I said, rational integer values attained by chi-q on rational 2 adic integer inputs. But what about irrational 2 adic integers? That is, integers z whose digits are not eventually periodic. What happens if chi-q of z is a rational integer for some irrational z? Before we answer this question, we need a technical result. This is chi-q of 0 chi-q equals 0 if and only if z equals 0. Since chi-q of 0 is 0 by definition, to complete the proof, we only need to show that chi-q is non-zero for all non-zero inputs. So by way of contradiction, suppose we have some non-zero 2 adic integer, which makes chi-q 0. Since z is non-zero, we can write it as 2 to the n times u, where u is some multiplicatively invertible 2 adic integer. In particular, it's an odd 2 adic integer, and n is some non-negative integer. Since u is odd, the functional equations of chi-q yield the following. So here it's chi-q of z, that's chi-q of 2 to the n u. Well, then we pull that out and get 1 over 2 to the n. Since u is odd, it's going to be of the form 2v plus 1 for some 2 adic integer v, so then we apply the odd branch and we get the following. Again, here is v is u minus 1 over 2. Solving for chi-q of v yields, just from this formula right here, yields that chi-q of v is negative 1 over q. However, negative 1 over q is not a q-adic integer. It has an absolute q-adic absolute value strictly greater than 1. Yet, as we saw, all of chi's q's outputs on the 2 adic integers are q-adic integers. So no such v can exist, therefore no such u can exist, and so no such z can exist, and we're done. With this proposition, we can now answer our question about what happens when chi-q becomes an integer on irrational z's. And this gets us the divergent points correspondence principle. Let z be an irrational 2 adic integer at which chi-q attains a rational integer value. Then that rational integer value is a divergent point. This proof, just as a reminder, this is going to be completely non-constructive. So let z be irrational and make chi-q of z into an integer. Since z is irrational, it can't be 0. So as we just saw, this tells us that chi-q of z is not 0. Now note that chi-q of z cannot be a periodic point. By the fanciest version of the correspondence principle, if this was a periodic point, then z would have to be an integer. It would have to be rational. The reason why we can conclude this is because there is a bijective correspondence between periodic points of H and the rational two-adic inputs that chi-q sends to those periodic points. So even if there are, and so not only does this say that there can only be a single value of z, which makes this into any particular periodic point, that z must necessarily be rational. But that is impossible. We're given that z was irrational. So purely by irrationality, chi-q of z cannot be a periodic point. So chi-q is an integer, which is not a periodic point. Now this is where that result about dynamical systems comes in. Since H is a self-map of Z, every integer is either a pre-periodic point of H or a divergent point of H. So all we need to do is show that chi-q of Z cannot be a pre-periodic point, in which case our classification of dynamical systems on the integers will automatically force this to be a divergent point. So by way of contradiction, let's suppose chi-q is pre-periodic. Then there's going to be some n greater than or equal to 0, such that H circle n of chi-q of Z is a periodic point of H, and necessarily a non-zero one at that, because we know that chi-q of Z is not 0, and the only integer that H sends to 0 is 0 itself. The proof here is the following idea. So where is it? Yes. So since this is going to be a periodic point, thereby our correspondence principle, there's going to be a rational two-adic integer, y, such that chi-q of y is equal to this thing. But here's the problem. So since all we're going to do is rewrite this like so. Let j be the string infinite length representing z. We have that chi-q of y is equal to the nth iterative h applied to chi-q of j. This is we can obviously, because this is an integer, that we can, instead of using h itself, there's going to be some string I of length n which gives the motions of chi-q of j under n iterates of h. Thus, we can rewrite this as h bold I of chi-q of bold j, and then we use the concatenation identity, the functional equation, to write this as chi-q of bold I wedge bold j. So bold I wedge bold j is necessarily since this is a periodic point, this number is the unique two-adic input which makes chi-q of equal to this quantity. So that means bold I wedge bold j must be y. But we have a problem here. Y is rational, so its digits are eventually periodic. Here, I is finite and j is infinite, and j represents z. But since z is irrational, j is never periodic. Thus, a finite string wedged with an infinite string, and the infinite string being aperiodic, this means this whole thing is never periodic, which means y is irrational. But that's impossible. We just saw that y has to be rational. This is a contradiction. So chi-q of z cannot be a pre-periodic point of h. So by our classification, this forces chi-q of z to be a divergent point. In particular, this argument also shows that strictly pre-periodic points can never occur in the image of chi-q. The only things that if chi-q spits out an integer, that integer is either a divergent point or a periodic point, and is never a pre-periodic point. So this actually immediately gives us something interesting to notice. It's conjectured, as I've mentioned before, for the certain qx plus 1 map, it's conjectured that when q is greater than or equal to 5, the set of divergent points in the positive integers that the map has density 1. So at almost every positive integer should be a divergent point, which means we should expect chi-q to take almost every positive integer value as z varies over the two adics. On the other hand, if the Collatz conjecture is true, then 1, 2, and 2 are the only positive integer periodic points of chi3, and so chi3 should take very few periodic points. Should take very few positive integer values. Indeed, yeah. So just there, we can say that even if we can just establish a qualitative control on the value distribution of the integers in chi-Q's image, we can use that to make conclusions about periodic points and divergent points. And I think it's quite likely that if we can show that chi-Q for q greater than or equal to 5 attains infinitely many positive integer values, that all but finitely many of them have to be divergent or something, because they assume that if we had too many cycles, that there would be a contradiction and something would fall apart. Anyhow, this having proved the one direction of the correspondence principle for divergent points, I can conjecture that the converse is true, that x is a divergent point of TQ if and only if there is an irrational 2-adic integer such that chi-Q sends that integer to our divergent point x, and this should say such that chi-Q of z is equal to x. So obviously, this conjecture would be really elegant if true, for it would show that both the periodic and divergent points of the shortened QX+1 map are completely controlled by chi-Q. This would cement the Numens place as the most significant object in Collatz studies next to the Collatz type maps themselves. Also, just to reiterate, everything that we have done here applies not just for basically all the one-dimensional hydra maps on the integers. It also applies for the multi-dimensional hydra maps, the ones on the rings of algebraic integers, as well as the positive characteristic hydra maps on the rings of polynomials with coefficients in a finite field, as well as the integer rings of algebraic extensions thereof. So this is very broad, and really the one advantage to using the string formalism is that really, other than changing the values of the subscripts of 2 and q or whatever, the proof can be copied almost verbatim. Because here you don't have any the fact that that the map has 2 branches, or the fact that the branches are of a particular form, that's all completely swallowed up by the string formalism that I'm using here. So this argument, it extends verbatim, and when you want to do the multidimensional case, you can, the way I did it in my dissertation was just by going from, was working from instead of working with scalars, I'd be working with vectors. So instead of bold J being a sequence of numbers, it would be a sequence of tuples. So yes, this is all really nice and really exciting and really fun. Now we get to talk about what's next and where we can go with this. We have horizons to consider. So before we end, I'd like to talk about some of the horizons that have opened up by what we've just done. So first is the Tao of Collatz. So of the 3 horizons I will be sharing with you today, this one, the first, is the most important. And the reason this is the most important is because it is a rare example of a case where you, the viewer, yes, you, can help me. I need you to get Terence Tao to watch this video. Ideally, I'd like him to watch all of my videos and read my blog posts and perhaps even read my dissertation, but as a start, just having him watch this video would do. The reason why I make this request is because of the not the reason why. The people that I am directing this request to are math students at UCLA, particularly ones who are in one of Tao's classes, as well as colleagues of Tao, either at UCLA or other institutions. Personal friends also work. So, remember how I said in episode 1 that what I discovered is completely new? Well, for the non-Archimedean analytical phenomena we saw in episode 1 with that weird point-wise dependence of topology of convergence, that the novelty is completely true. However, for the stuff we've been doing in this episode, it's not quite fair to say that it's new. And I don't just mean Baum and Sontachi. The first versions of the ideas, results, and arguments that I've shared with you today came to me in winter of 2019-2020. At the exact same time, late 2019, October if I recall correctly, Terence Tao released to arXiv a paper entitled Almost All Orbits of the Collatz Map Attain Almost Bounded Values. he's gone to talk about this paper all over the place. He has a video lecture from the Institute for Advanced Study, etc. I've included a link to it in the paper in the description below. So in this paper, what Tao uses probabilistic techniques in a novel way, and the centerpiece of this are what he calls Syracuse random variables. In his notation, he writes that this is a family of random variables indexed by n, and it's Sirac of z mod 3 to the nz, where, just like me, z mod 3 to the nz is a shorthand for the integers from 0 to 3 to the n minus 1. So, in nearly all respects, Tao's work has nothing to do with mine. It's all probability theoretic. And I'm not really that good in probability theory. It's very, very dense and detailed and incredible. And so, also it uses real and complex numbers, whereas I'm using p-adic numbers. So in that respect, it's almost essentially completely different. But there's one way, and it's a foundational way, in which my work overlaps with his. And it's that we both use chi3. And as far as I know, Tao's work is the only other occurrence of chi3 in the literature outside of my own. So his idea goes like this. The SRVs provide a probabilistic model for the dynamics of the Collatz map. And just like me, in the opening pages of his paper, he derives these random variables by considering the constant term of what happens when you compose branches of the Collatz map multiple times. For each n, Sirac of z mod 3 to the nz is a discrete random variable taking values in this set. This should be a minus, which we can treat as a ring, but we can also just treat it as a set. And what his argument does is he compares the SRVs to random variables that he builds up using tuples of geometric random variables. And his main tool for making this comparison is the total variation distance for two discrete random variables. And just to recall, let R be a discrete subset of the reals given two random variables x and y, both of which take values in our set R. The total variation distance between x and y, denoted dTV of x and y, is defined by the sum of the absolute values of the probability that x is equal to R minus the probability that y is equal to R. In certain respects, you can think of the Syracuse random variables, as my work and Tao's work shows, as they're basically the best probabilistic model of the Collatz map's behavior. What he ends up doing is that he treats the SRVs as a two-dimensional renewal process and is able to attain sufficient control over the Syracuse random variable's probability mass functions to prove the conclusion stated in his paper's title, that almost all orbits of the Collatz map attain almost bounded values. Now, at a glance, again, as I said, this looks like it couldn't be less related to my work. It seems impossibly far removed for it. Indeed, reviewers at the prestigious Journal of Number Theory told me to remove my mention of the Syracuse random variables in an abstract of an early version of my Part 1 paper because, as they saw it, chi3 had nothing to do with random variables. Obviously, they were wrong, but it's completely understandable why they made this mistake. Really, what I'm doing is incredibly, incredibly weird, and you basically have to be insane to see things the way that I do, the way I do. So, with the exception of additive combinatorics, which studies, among other things, random variables taking values in finite abelian groups, like z mod 3 to the n z, random variables are basically, they're almost always going to be real valued things, not three-adic valued things. Sometimes you might get a complex valued thing, but a complex valued thing is just two real valued things. So the thing is, chi3 can be viewed as a random variable taking values in the three-adic integers. I said that chi3 can be viewed as a random variable in the abstract of the early version of this paper, and I didn't explain it more than that. Here is what I meant. Given any three-adic integer y, and any integer n greater than or equal to 1, we can consider the preimage of the set of the neighborhood of radius 3 to the n of y. We consider its preimage under chi3. this is going to be the subset of the two adic integers on which chi3 attains values congruent to y mod 3 to the n. Since this set absorbs everything past the 3 to the n in this 3 adic integer, we can restrict our attention to the value of y mod 3 to the n, which is going to be some x in this set. So, since it's in this, because we have the following equality of this of sets if and only if x is congruent to y mod 3 to the n. It's relatively easy to show that as a subset of Z2, the preimage of this set is sorry, this is wrong. So it can be easy to show that this set is measurable with respect to the two adic hard probability measure on the two integers. And by here I mean the real value. You can do this by topological arguments or by direct computation. So in doing so, we get a random variable out of chi3. What we do is we feed it a 3 adic integer and an n, and then we can compute the probability of that chi3 is congruent to our chosen 3 adic integer mod 3 to the n. With a little work, it is straightforward to show that chi3 is actually equivalent to Tao's Syracuse random variables. Specifically, we have the following. The probability that the nth Syracuse random variable is equal to some x in z mod 3 to the nz, that's the same thing as the probability that chi3 is congruent to x mod 3 to the n. This is the 2 adic probability measure of the set of 2 adic integers which chi3 sends to values congruent to x mod 3 to the n. Indeed, Tao actually explicitly mentions early on in his paper, in remark 1.13, he says the following. One could view the Syracuse random variables, Sirac of z mod 3 to the n, as projections, Sirac of z mod 3 to the n z, of Sirac of z3 mod 3 to the n, of a single random variable Sirac of z3 taking values in the 3 adics, which he defines as the direct limit, blah, blah, blah. However, we will not explicitly adopt the 3 adic perspective in this paper, preferring to work instead with the finite projections. As I'll mention more about in a bit, I figured out this connection between my work and Tao's in the summer of 2020 when, waist deep in my explorations, I did a detailed computation, and then while perusing Tao's blog post about his paper, I noted that the values of the probability mass function for Sirac, this should be a 3 squared of z, he lists these numbers, both on his blog post and his paper, and these were the exact same numbers I'd gotten from my computation. After that, it was once I realized that what it was doing and what the implications of this were, it was a simple matter of working through the Fourier theoretic details to prove that my methods are equivalent as his in terms of the foundational idea of chi3 or the Syracuse random variables. When I sent my paper to the Journal of Number Theory, I thought that the recipe that I described above for realizing chi3 as a 3 adic valued random variable was obvious enough not to need an explanation. For every, you pick an n and you pick an x between 0 and 3 to the n minus 1, and then you compute the probability that x is congruent to x mod, chi3 is congruent to x mod 3 to the n minus 1, and by integrating that set over the 2 adic integers. So in my assumption that this would be obvious, that's where I made my mistake. And I suspect a major part of the reason why the folks over at the Journal of Number Theory didn't see this connection as obvious is because of how it flies in the face of orthodox procedures in probability theory. As is well known, the first rule of Fight Club is don't talk about Fight Club. Similarly, the first rule of probability theory is don't talk about the sample space. Remember that formally, thanks to Kolmogorov, we define random variables as functions on a sample space. The sample space is going to be a sigma algebra of sets. They're going to be our measurable sets. In this case, the probability density function of a random variable is actually the radon-Nikodym derivative of the measure that our random variable introduces on our sample space. Our sample space, since we're working in a probability space, we don't just have a sigma algebra of sets, we also have a probability measure, d mu. And then, in this case, we can then integrate our random variable times d mu, and then that's our density function times d mu, and then that gives us the measure induced by our random variable. And so this derivative is, again, as I said, is taken with respect to whatever probability measure our probability space comes with. However, in practice, probability theorists almost never think about random variables in this form. Indeed, we call them random variables, not functions, because and so we think of them as we ignore their identity as functions of a sample space valued variable. In fact, it's in that regard, you can say it's actually quite surprising that for this particular random variable, the Sirac of Z3, that viewing it as a function on its sample space yields a result as useful as the correspondence principle. So for chi3 here, we can think of the sample space as going to be the usual Borel sigma algebra generated by the open sets of Z2. And with the measurable sets being the Haar measurable sets. And again, we can think of chi3 at individual points, but we can also treat chi3 as a probabilistic object by asking for the measure of the sets on which it attains a certain range of values mod some power of 3. So in Tao's own words, the most difficult result he established in his paper, and indeed the heart of his proof, is an explicit estimate for the decay of the Syracuse random variable's characteristic function. This is also the reason why I stopped calling the Newman the characteristic function, because then I would have to talk about the characteristic function of the characteristic function, which is messy. So to rewrite what Tao did in using my formalism, as here I'll do what I did in my dissertation. First, we're going to define a complex valued function, phi 3. It's from the Z3 hat. That's the rational numbers in the unit interval with whose denominators are power of 3, and we equip it with addition modulo 1. Here, the brackets with a 3 around them are the 3 adic fractional part, and dz is the real valued Haar probability measure on Z2. If you're worried that this integral doesn't exist, you don't need to be. For any given t, this is going to be some triadic rational with some number on top and then a power of 3 in the denominator. This then means that the value of chi3 only matters modulo whatever the denominator of t is. So for example, if t is 1/3, then the only thing chi3 will contribute will be either 0, 1, or 2 based on its value mod 3. And as a result of this, you can show by directly computing the preimages of sets that for each individual t, this function is going to be measurable. And since it's also continuous, since it's going to be measurable, and since we're working over, and it's bounded everywhere because it has unit absolute value, we can then integrate it and everything works fine. So Tao's decay estimate is proposition 1.17 of his paper, and he writes this integral as an expected value. And he says this: let n be greater than or equal to 1, and let c be in z mod 3 to the n z and not divisible by 3. Then the expected value of e to the negative 2 pi I c Sirac z 3 to the n z over 3 to the n is Vinogradov less than a n to the negative a for any fixed real number a greater than 0. This is the Vinogradov notation, which means that it's big O of n to the negative a as n approaches infinity, where the constant of proportionality depends on a. In my formalism, I would write this as follows. Let n be greater than or equal, this should not be an n, it's, ignore this. So for any real number a greater than or equal to 0, there is a constant c depending on a such that the absolute value, the complex absolute value, of phi 3 of t is less than or equal to c divided by negative v3 of t to the power of a. Negative v3 of t is the exponent of 3 in the denominator of t. It's always going to be positive, and here we require t to be non-zero. So, yes, and this gives a nice decay rate as the 3 adic absolute value of t grows. I personally think this is a lot prettier than this, but that's just me. So with a phi 3, we can express the probability that chi3 is congruent to x mod 3 to the n by applying a discrete Fourier transform. Here, the probability that chi3 is congruent to x mod 3 to the n is equal to 1/3 times this times the sum of phi 3 of t e to the 2 pi I x t, where we sum over all t in z3 hat with denominators at most 3 to the n. And indeed, applying this Fourier inversion formula to this will then immediately produce the integral formula for phi 3 of t, which shows that phi 3 is the characteristic function of pi 3. So, as I said, I noticed the parallels between my work and Tao's when I was waist deep in a computation. Well, here's that computation. Using chi 3's functional equation, we can get a functional equation for phi 3. This is obtained, but what we do is we take the integral for defining phi 3, and then we split it up, integrating it over 2z2 and 2z2 plus 1, and then we make a change of variables to get the following expression, to which we then apply chi 3's functional equation to simplify these into expressions in terms of chi 3 of y, and then this frees us to solve the right-hand side in terms of phi 3 of t. We'll then obtain a recursive formula for phi 3 of t, which we can solve to get the following, which is a very nice thing. And then applying the discrete Fourier transform to this thing, as I said, will then give will then give us a recursive formula for the probability, which is, we know, is the probability that the Syracuse random variable, the nth one, is equal to x. And so Tao's formula from his paper is lemma 1.12, and it's this thing. And if just by looking at this, you can see where the things are similar. Here, the 3 adic absolute value of t is going to be 3 to the n, so this is going to be 3 to the n minus 1. If t has 3 adic absolute value 3 to the n, and Tao uses n plus 1, so that's why this is big N. If this is just n. If this was just an n, this would be n minus 1, much like we would have here. So we can then so now back to my plea for help. You see, and this is quite ironic, but I went to UCLA as an undergraduate. Indeed, I have lived my entire life in Westwood, California, in my family home. It's a sub-community of Los Angeles, and it's within walking distance of campus, UCLA. And indeed, that's where I am right this very second, as I record this video. I tried for years to get Terry's attention. My latest attempt was an email sent on December 14th to Marcus Keel at the University of Minnesota. I was told Keel is a personal acquaintance of Tao, and that he's nice, when he's not busy, and that I might as well try to get him to help hook me up. Keel has yet to reply to me, nor has the guy at Georgia Tech that I emailed. So yes, people don't reply to me, and it's awful. From what I understand, Terry has a filter on his email account, which automatically takes any email that he gets with the word Collatz in it, and it puts it into his spam folder. As a result, I can't mention my research. I can't even mention his research without guaranteeing that my message will go straight to the spam folder and he'll never see it. So, yes, this is very tragic, very ironic, and it's incredibly frustrating. So much so that I've so invested myself in this that right now all I want is just some kind of acknowledgement that I've done something, that I exist in general. Maybe a couple of sentences, and by sentences I mean complete sentences, not journal referee speak, about what he thinks of my work or where it could go next. If he really wants to make me feel good, he could say or write nice things to and or about me, like "good job, Max," or "wow, this is really amazing," or something like that. Don't worry, I'll get into more detail about my general grievances at the end of this video. Also, as a final non-ego adjacent note, it would be interesting if we could use the F series for chi 3 and plug it in, the one that we started the episode 1 with. If we plug it into this formula here, and could we perhaps use it to get a better approximation of this oscillatory integral? Who knows? So yes, there's that. And yeah, so now we have our second horizon, which is the converse of the correspondence principle for divergent points. So with my personal frustrations about Tao thus fully vented, we can now move on to discuss the CPDP. Also, Terry, if you're watching this, thank you so much. And also, you're great. Keep being great, etc. So anyhow, we're going to begin with the following characterization of how chi q interacts with theta 2, that 2 adic shift map. And it's the following. Given any 2 adic integer z, if we take chi-q of the shift of z and apply the branch of h dictated by the digit that the shift removed, that's the same thing as applying chi-q of z, chi-q to z. So let's just write Cn to be the nth two-adic digit of z. Then we can write z as, well, here's its first digit, the 0th digit, and then this is 2 times everything else. This is 2 times z minus z mod 2 over 2. This, of course, is just phi 2 of z. This is going to be an even two-adic integer if and only if z is even, and it's going to be an odd two-adic integer if and only if z is odd. If z is even, we can then write chi of z, we can multiply and divide by 2, and this is 1/2 chi q of z over 2. If z is odd, on the other hand, we can do this because we know that this is going to be an integer, and then we get the following. We can combine these two formula and into a single one by writing this, where recall h0 is x over 2, and h1 is qx plus 1 over 2, and this is the theta 2, and we're done. Now, suppose we have an irrational two-adic integer z0 that chi-q sends to an integer. Then, by the correspondence principle, setting x0 to be that integer, we then have that x0 is a divergent point of tq. If z0 is even, note what happens. x0 is chi-q of z0, which by the formula we just proved is h0, because z0 is even, times chi-q of the shift of z0. Here, since the h0, we were just writing out the definition of h0, we get this. So, look what happens. If we multiply by 2 on both sides, I then get that 2x0 is equal to chi-q of the shift of z0. Since x0 is an integer, so is 2x0, and so this number here is also an integer, and since z0 is irrational, so is its shift, and as a result, by the divergent points correspondence principle, this is going to be a divergent point of tq as well. The same thing happens if z0 is odd. Here we then get the following, and so since this is an integer, this is going to be a 2x0 minus 1 over q. Since chi-q is a map from z2 to zq, and since z1, which makes chi-q equal to this thing has to be a q-adic integer, which means that its q-adic absolute value has to be at most 1. This forces 2x minus 1 to be congruent to 0 mod q, otherwise this would not be a q-adic integer. So, since this condition occurs, and since x0 is an integer, this is not just a q-adic integer, but a rational integer. It's an ordinary integer as well. And so once again, whether or not z0 or z0 is even or odd, if we apply the shift operator to it to get z1, chi-q of z0 being a divergent point forces chi-q of z1 to be a divergent point. What this shows then is that once we have an irrational two-adic integer, which chi-q sends to a divergent point, applying the shift operator to that two-adic integer will then give us a value that chi-q sends to another divergent point. So in particular, we have shown the following. Let q be an odd prime. Then, the set of irrational two-adic integers that chi-q maps into the integers is invariant under the left shift operator. Now, remember when I said that theta 2 is the quintessential example of an ergodic map on the two-adic integers. If we can show that this is inequality, that's going to get that we could then potentially conclude that this set is going to either have, by the ergodicity of phi 2, we can then conclude that this set either has measure 0 or measure 1 in the two-adic integers. Now, what about if we go backwards? So when we went forwards in the subscript, making it bigger, we deleted digits. So going backwards, making our subscript negative, would mean adding a digit. So we can write z1 as it's either 0 or 1 plus twice z0. So then we're going to define x minus 1 as chi-q of z minus 1. Going through the motions, we then get that x negative 1 is this, and if x0 is in z, one and only one of these two branches can be an integer, in that this occurs precisely when the value of z negative 1 mod 2 is the same thing as the value of x0 mod 2. So then we go about this procedure recursively, and then we end up with the following. Fix 0, 0 in z2, and let x0 be chi-q of z0, and for each n define, and greater than 1, define zn as the nth shift, and xn is the image of zn under chi-q. If z0 is irrational, and x0 is an integer, we can then construct this trajectory, this, actually, is it forwards or backwards? I forget. But anyhow, we get the following. Xn is in z for all n. Xn is a divergent point of tq for all n. Tq sends xn plus 1 to xn. Xn is equal to h value of zn mod 2 of xn plus 1, shifting zn to zn plus 1, and zn is equal to this thing. So, letting n be greater than or equal to 0, what we have is that the x negative n is the nth term of the forward orbit of x0 under tq. So note, this is important. The forward orbit of x0 is uniquely determined. And as we saw here, once we have x0, the values of the z negative n's are completely determined by the x negative n's. So there's only one way to extend this. On the other hand, xn for positive n is going to be an element of the nth pre-image of x0 under tq. And so in this respect, what we have is like a sort of conveyor belt, where shifting the digits of z0 to the left corresponds to applying an inverse image of tq. On the other hand, if we shift the digits of z0 to the right, we would need to pick the new leftmost digit of this shifted number. However, as the above shows, our choice is completely determined by the image of x0 under tq. 6 is of particular interest here because it shows that if x0 is irrational, as if z0 is irrational and makes chi-q of z0 into an integer, then the xn's are completely determined by z0. These xn's, I said, correspond to a particular choice of a backward orbit of x0, and indeed the nth two-adic digit of z0 is the index 0 or 1 of the nth branch of tq, which we would use to go from xn to xn plus 1. So using chi-q in this way, we can pass from studying the divergent trajectories of tq to the behavior, to subsets of z2 under the shift-to-adic shift operator. So let x0 be an integer and be a divergent point, but let us not assume that x is a value attained by chi-q. What 6 does is it actually suggests a way of constructing a z0 so that chi-q of z0 equals x0. Note, if we could do this, that would then prove the correspondence principle for divergent points, its converse. So we're going to take as our ansatz, our guess, that z0 is the two-adic integer whose two-adic digits are the values of xn, the pre-image, mod 2. And so our guess is this. However, there's going to be a problem. Again, these are, as we make k bigger, we have pre-images. So as we said, there's no unique way to do this. There's infinitely many ways to do it. And indeed, given any x0, we can have I will say that the backwards orbit under tq of x0 is degenerate if at every stage we just picked the even branches inverse and just kept multiplying by 2. As long as we allow for any possible choice of a backward orbit of x0, note that we can then choose the degenerate backward orbit x0 equals this thing, in which case z0 would be equal to 0. Although this might seem to indicate that the converse CPDP is flawed, this isn't actually the case. The converse CPDP is the statement that every divergent point of tq is the image of chi-q at some irrational two-adic integer. The fact that, given a divergent point x, there exist degenerate choices of backwards orbits such that z0 is an element of n0 does not rule out the existence of some choice of backward orbit of x0 such that this thing is an irrational two-adic integer. Also, now another issue of interest and relevance to all this is that while it's easy to show from the functional equation that the restriction of chi q to n0 is injective, indeed Tao comments as much in his paper, the extension to the two adics is no longer going to necessarily be injective. And so as an example, let q be a Mersenne prime with q equals 2 to the n minus 1 for some n greater than or equal to 1, then we can prove that z2 to zq is not injective. So let q equals 2 to the n minus 1. Then, if we consider chi q b2 of blah, 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 we get this. This is just by reasoning through the definitions. Since q is 2 to the n minus 1, 2 to the n minus q is going to be equal to 1. So if q is a Mersenne prime, then by with this form, then by considering b2 of 2 to the n minus 1, that number, that two-adic integer, will always be sent by chi q to 1. So now, what if we multiply this number by 2? Well, if we multiply this number by 2, then Chi's functional equation says that it's the same thing as dividing by 2. And so that's 1/2, because this is 1. Note that this is completely okay because this is still a q-adic integer, because the denominator is co-prime to q. Also note that b2 is going to be, of 2 to the n minus 1, is going to be in z2 prime. On the other hand, chi q of 1 is equal to 1/2, and so chi q of 1, which is equal to chi q of b2 of 2 to the n minus 1, which is 1/2, yet these two are different, so chi q is not injective. More generally, it seems plausible, but I do not know how to prove it, that chi q is not injective for any odd prime p. In fact, returning to our discussion of the converse CP-dP, a proof of the converse CP-dP would automatically follow if we can show that chi q is not injective. Let x0 be a divergent point. Let xn be any So the reason why this follows is if chi q is I got it wrong. Sorry. It's the other way around. It's not that injectivity would prove this, would prove the converse CP-dP. It's that the converse CP-dP would prove the non-injectivity. Indeed, and the reason for this is because from this 6 over here, that weird one, we guessed that let x0 be a divergent point of t and let xn be any non-degenerate backward orbit. Then the z0 defined by this guess satisfies chi q of z0 equals x0. That's my guess. And because any x in z will have infinitely many backwards orbits under tq, and in particular it will have infinitely many non-degenerate backward orbits, in most cases, however, there might, if x is a multiple of q, then that won't work. But just it seems plausible that that if we can prove this, then this implies conjecture 6, because it then tells us that if it has infinitely many backwards orbits, we can choose infinitely many backwards orbits that are non-degenerate, and each of which will give us a z0. So what it really is saying is that if this conjecture is true, the chi q is multi-valued at x0 precisely when x0 is a divergent point. The periodic point correspondence principle tells us that at any periodic point of tq, chi q is going to automatically be injective. There is one and only one two-adic integer that chi q sends to any given periodic point of tq. So this then, so to remember that we say that, given two sets x and y and a map f from x to y, we say y is a branch point or ramification point of f if the preimage of y under f contains at least two elements. So in this, my conjecture then is as follows. X is a divergent point of tq if and only if x is a branch point of chi q. And again, the idea here is that for every possible backwards orbit, we get a different input which chi-q sends to our divergent point. If we can get this much mileage out of chi-q, it would not be far-fetched to presume we could use chi-q to make conclusions about the dynamics of the extension of tq to z2. Studying tq on z2 is arguably even more frustrating than studying it on the integers due to the following extraordinary fact. My citation for this comes from Ligarius and Kontorovich's 2009 paper, Stochastic Models for the 3x plus 1 and 5x plus 1 problems. The links are in the description. And it's the following wonderful fact. So let q be any odd prime. Then the map tq on the self-map of the two adic integers is a homeomorphism of z2 and is measure preserving with respect to the real valued hard probability measure. In fact, tq is topologically conjugate to the two adic left shift map. That is to say, for each q, there is some homeomorphism of the two adic integers, such big phi q, such that big phi q of theta 2 of big phi q inverse is equal to tq. So this makes tq into an ergodic map on z2, and moreover, note that here, since this works for any prime, this makes tp and tq topologically conjugate to one another over z2 for all odd primes p and q. And this map, we can even write it down explicitly. Ligarius and Kontorovich, they have the formula for it. So what this says is, even though T3 is conjectured to have only 1, 2 as its cycle and send all other positive integers to that number, and even though it is conjectured that TQ, for q greater than or equal to 3, should send almost every positive integer to infinity, if we consider TQ and T3 on the two adic integers, their dynamics are topologically equivalent. So that's why looking at TQ over the two adics is useless, because we just lose all of the information when we complete things two adically. So, as kids these days might say, this fact is very cursed. So, that being said, our conjectures about chi-q's relationships to divergent points of TQ make it seem reasonable for us to expect the following. Let x be both a two adic integer and a q adic integer, meaning that it's a rational number whose denominator is coprime to both 2 and q. Then the following are equivalent. X is not a pre-periodic point of tq in the two adics. There exists a z in the irrational z such that chi-q of z is equal to x. X is a branch point of chi-q, and the pre-image of x, the fiber of x under chi-q, contains infinitely many elements. Now, we can also go further. We can make an even more unconventional topological observation. So in this idea here, we can think of chi-q's image in zq as being a kind of curve. And so what this conjecture, and the conjecture about the ramification points, what this is then saying is that I'm conjecturing that this curve will have a self-intersection if and only if the TQ has a branch point. I mean, not a branch point, has a divergence point. We can do this another way by mapping the two adic integers onto the unit interval. This map here, eta 2, it is surjective, but it is not bijective. And here, the CNs are going to be elements of 0, 1. We can then get a curve, chi-q of eta 2 inverse. This is a genuine curve. It's from 0, 1 to zq. And the functional equations for chi-q then give a monoid of self-symmetries for cq here. This curve is essentially a de Rham curve in ZQ, and except that as maps, the branches of TQ are not both contractions of ZQ. Rather, the even branch is a contraction of the reals, and the odd branch is a contraction of the Q-adics. As Alain Robert says in his course in p-adic analysis, he discusses eta 2 and other linear models of ZP in its opening chapters. He points out that for any t in 0, 1, there are at most two adic integers eta 2 with two adic integers which eta 2 sends to t. And so in that mind, conjecture 8 is the assertion that the divergent points of TQ are precisely the points in ZQ at which CQ has a self-intersection of multiplicity at least 3. These scare quotes around the word curve here are due to the fact that chi-q of t is not continuous, since chi-q isn't continuous. However, the rising continuity condition of chi-q is easily seen to be equivalent to the left continuity of CQ, meaning that for any strictly increasing sequence Tn in 0 to 1 that converges to T, this limit holds. Regardless of whether we choose to view the image of chi-q as being parameterized by Z2 or as being parameterized by 0, 1 via CQ, it seems appropriate to call this set here a curve. And in fact, we can really justify this because even though chi-q is not continuous in the traditional sense, we can recover continuity if we equip Z2 with an exotic topology. This exotic topology is an example of a more general construction for ZP, which makes rising continuous functions into bona fide continuous functions. So let P be a prime. Then I define the rising topology on ZP as the topology generated by the following sets, which by definition means that all of these sets are open in our topology. We have the base of open sets for the p-adic topology, and so that means the rising topology is strictly finer than the p-adic topology, and the extra open sets we have are the non-negative integers, and then sets of the following form. It's some z with infinitely many digits, and then we take the union of all of its projections mod p, mod p to the n, where n is bounded from below. I write script trc to denote the rising topology, and write zp comma script trc to denote the topological space obtained by equipping zp with the rising topology. Note that these sets here are going to be both open and closed in ZP, in the rising topology. As we will see, the rising topology is an example of what is known as an initial topology. Let x, so as a definition, let x be a set and let y be a topological space. Let I be an index set and let script f be a family of functions indexed by I. These functions are from x to y. Then the initial topology on X, induced by script f, is the topology in which the open subsets of X are precisely those which are generated by arbitrary unions and finite intersections of sets of the form fi preimage of V, where V is open in Y and where I is an index. Consulting Wikipedia, and I believe that this comes from Bourbaki's general topology, although the Wikipedia article also has work of Grothendieck's on there. Amazingly, I could potentially be citing Grothendieck for this, despite the fact that we couldn't be more different as mathematicians. So let X be a topological space, and with topology T, given an index set F, and for each I a topological space yi, and a map fi from X to yi, let F be the collection of our maps. We say that F separates points from closed sets if for all closed sets C in X and all X, little x, in big X but not in C, there is an I, so that Fi of X is not contained in the topological closure of Fi of A. And then from this we get a following theorem. Let X be a topological space with topology T, then given an index set, and blah, 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 blah. Then F separates closed points in X if and only if sets of the form Fi inverse of V for I in I and open V in Y form a basis of T for T. That is, every open set of T is expressible as a union of sets from the basis. And so combining this result with this thing, we get the following a corollary. That suppose F separates points from closed sets in X, then the topology on X is the initial topology induced by F. So using this thing, we can show that the rising topology is the initial topology generated for any given rising continuous function chi. Also, let P and Q be distinct primes, and recall we write C twiddle of ZP QQ to denote the space of rising continuous functions from ZP to QQ. Then the rising continuous topology on ZP is the same thing as the initial topology induced by the rising continuous functions. So we're going to argue using theorem 9 to prove that corollary 4 applies. To do this, we just need to show that the rising topology and the initial topology induced by rising continuous functions are the same. So to do this, first, to show that the rising continuous function's initial topology generates the rising topology, it suffices to show that each one of the sets that generate the rising topology are expressible as unions of the sets of the form F preimage of V, where V is Q-adically open and F is rising continuous. So we need to construct examples. So first, the easy part is every continuous function is rising continuous, and so by continuity, we can then, if we pick a continuous function and for an open set, the preimage of that will be expressible as a union of these open balls. So we don't need to deal with this. We only need to deal with sets of the form 2 or 3. So first, let's let n be a non-negative integer. Now consider the following function. We go from z and zp, and then we output 0 if z is not equal to n, and 1 if z is equal to n. This is going to be rising continuous. I'll leave it to you to verify. It's straightforward using the definition. This function's image is 0, 1, so let v be open in QQ. If v contains 1 but not 0, then the preimage of v under this function is n, so that makes n open. If v contains 0 but not 1, then the preimage of v is zp take away n. Thus n and zp take away n are both open, which means n is both open and closed in the initial topology induced by rising continuous functions, which is exactly the case as in the rising topology. Now we need to deal with those sets of this form. So for an arbitrary a with infinitely many p-adic digits, let's set f to be the following function. It is 1 if z is equal to a, and it is also 1 if z is equal to a mod p to the n if n is greater than or equal to n. This series always converges, but pointwise, not uniformly, because for any z, at most one of these brackets can evaluate to 1. So this, again, it's easy to show from the definition that this is rising continuous, and it takes the values 0 and 1. And since f preimage of v is equal to this set for any v in QQ, which is of a sufficiently small open neighborhood of 1, this proves that this set is open in the technically this should be a, not z. My bad. This should be a, not z. This should be a, not z. So this proves that this with a is open in the initial topology, and the same is then, and by taking an open neighborhood of 0, we get the same for the complement of this set. So that, again, with z replaced by a, and so that means that this set is both open and closed, exactly as what we get in the rising topology. So the initial topology from the rising continuous functions generates the rising topology. Now we need to show the other side, that the rising topology generates a rising continuous initial topology. To do that, we need to show that for any rising continuous function f and any open set v, the set f inverse of v is, well, f preimage is open in the rising topology. So letting v and f be as given, there are going to be two cases. The first is that the preimage of v under f has an disjoint from zp prime. This then forces the preimage of v to be an element, to be a subset of the non-negative integers, and so we can automatically write our preimage as a union of singletons. These singletons are open in the rising topology, which then makes the preimage of v under f open in the rising topology. So the second case then is when the intersection of f inverse of v with zp prime is non-zero. Letting z be in this intersection, by f's rising continuity, this number is going to converge to f in q-adically as n goes to infinity. Remember that convergence isn't just defined with limits, we can also define it topologically. And in particular, a sequence converges to a point topologically if every sufficiently large term of the sequence is contained in some open neighborhood of our point. So since v is open in QQ, topologically the definition of convergence of the projections to f of z forces f of zpn to be contained in v for all sufficiently large n. Applying preimages, we see that f of z mod pn contained in v occurs for all sufficiently large n is then the same thing as the projection of z mod p to the n is contained in the preimage for all sufficiently large n. And so the preimage of V under F, it contains Z as well as all these preimages, which is an open neighborhood of Z in the rising topology. And note that we can do this for every single Z that's in this intersection. And so for every single Z in the intersection, we then take the union of all those sets. They're all open in the rising topology. So then this intersection is then open in the rising topology. And then we add any remaining singletons necessary to fill everything up. And then once again, we get a set that's open in the rising topology. So the two topologies are the same. And we're done with that. So this then gives us a topological characterization of rising continuity. Let P and Q be distinct primes, and let QQ be equipped with the usual Q-adic topology. Then a function from ZP to QQ is rising continuous if and only if it is continuous when ZP is equipped with the rising topology and QQ is equipped with the Q-adic topology. And now I am going to take a brief break because my jaw is getting sore. My computer is angry at me when I do this, so mute. And, oh, no, I know why, because I'm in preview. There we go. Go to QuickTime Player and pause. All right, and we're back. So I should mention that the stuff about this, topological stuff here is not in my dissertation. It is new. I got help with it from the wonderful people over at Anthony Vasutoro's A Modern Number Theory Discord, so I give a shout out to them. And before we move on to our last horizon, there's one more interesting construction worth discussing. So so fix an odd integer x in Z and let xk be the kth iterate of x under H. Then, setting z0 equal to 0, define zk plus 1 to be 2 times zk if xk is even, and 2 times zk plus 1 if xk is odd. Then we can write that zk will be equal to the sum from n equals 1 to k of xk minus n mod 2 times 2 to the n minus 1. Just flipping around the summation and writing this out, we then get the following. It's going to be x to the xk minus 1 mod 2, xk minus 2 mod 2 times 2, blah, 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 all the way up to x0 mod 2 times 2 to the k minus 1. So in other words, the earliest terms of our x sequence are given the least amount of 2 adic weight, whereas the kth minus 1th term is given the most 2 adic weight. Taking 2 adic absolute values, we get that this thing has 2 adic absolute has a 2 adic absolute value at most 1. So this is so the zk's are a bounded sequence in the 2 adic integers, and since the 2 adic integers are compact, we can extract the subsequence which converges 2 adically to a limit z infinity. So now let's let S be the sequence of zk's, and let S bar be its topological closure in Z2. If x is a pre-periodic point of H, which is eventually sent to a cycle, omega, observe that S bar take away S is then equal to the pre-image of omega under chi q. The proof is straightforward. As I said here, only the early iterates of x get small 2 adic weight, and so as k approaches infinity, only the long-term behavior of x iterates mod 2, i.e. x's parity vector, will matter. And so, in other words, the parities of the x's first few iterates will be forgotten by zk as k goes to infinity, because as k goes to infinity, the contributions to zk from those first few iterates will decay to 0 2-adically. In particular, if x is eventually periodic, then the xk's will eventually become periodic, and so zk digits will eventually become periodic. So here then S bar take away S is then the set of subsequential limits of the zk's, meaning it's anything that you can get by taking the limit of some subsequence of S. And in particular, given any z in S bar take away S, by corollary 3, we'll be able to obtain any other any other element of S bar, take away S, by applying a cyclic permutation to these digits, two-adic digits of Z. And moreover, any such permutation of those digits will be an element of S bar take away S, and then this proves that S bar take away S is actually going to be equal to chi q as preimage, to the preimage of omega under chi q when we let this go to infinity. And so, in other words, what it's saying is, if we consider this process like a seeding process, if we seed it with a pre-periodic point, then the set of subsequential limits we get is equal to the set of inputs that chi q sends to omega. So this seeding algorithm generates those two-adic integers which chi q sends to the cycle which x is eventually sent to. This suggests that you should be able to do something similar for the divergent points. In particular, if x is a divergent point of q, and if v is the irreducible orbit class of tq, which contains x, then if we apply the above construction to obtain zk and s bar, then s bar take away s is the subset of two-adic integers which chi q ascends to v. If we could prove this, we would then get a proof of the converse for the divergent point principle. Morally here, really what we see is that given an x and in the integers, we have two kinds of data that we can get from it: arithmetical data and dynamical data. When x is a periodic point of q, of tq, associated to some cycle omega, then the data associated to x is the Bohm-Sontachi Diophantine equation that characterizes x. Equivalently, it's the formula chi q of n divided by 1 minus mq of n, which is equal to x. The dynamical data, on the other hand, is chi q's preimage applied to a big omega, which is the set of rational two-adic integers that a chi q maps bijectively onto omega. On the other hand, when x is a divergent point of tq, by that the dynamical data would be the elements of s bar take away s. The arithmetic data, meanwhile, would be the right-hand side of the conjectured equality chi q inverse of v equals s bar take away s. The proof of the correspondence principle for periodic points depends on the fact that in the periodic point case, the elements of s bar take away s are related to one another by cyclic permutations of their two-adic digits. This dynamical transformation of chi q's inverse of big omega then corresponds to an arithmetic transformation of the associated Bohm-Sontachi type Diophantine equation, thereby yielding an equation for a different periodic point. That being said, it would be interesting to see what kinds of arithmetical invariants we can associate to s bar take away s in the divergent point case. Maybe some kind of two-adic irrationality measure of the elements, or something having to do with their digits. Is s bar take away s measurable with respect to the real valued hard probability measure on Z2 in the divergent point case? If so, what is its measure? And so on. As usual, there is a heck of a lot to be done. Finally, we have implications for transcendental number theory. So as I mentioned back in episode 2, prior to my own work, the only significant connection Collatz was known to have with other areas of mathematics were in transcendental number theory. It is well known that any proof of the weak Collatz conjecture should be reducible to a significant advancement in the current technology in transcendental number theory. As the name would suggest, one of the main goals of transcendental number theory is proving that numbers are, in fact, transcendental. This is, in general, very difficult. However, transcendental number theory does more than that. In particular, it studies the algebraic independence of numbers, which is whether you can whip up a multivariable polynomial that, when evaluated at a given tuple of numbers, yields 0. And it's also related to matters of Diophantine approximation, rational approximations of irrational numbers. One very fruitful area of transcendental number theory involves the study of what are called linear forms of logarithms, or linear forms in logarithms. These are expressions of the form beta 1 ln alpha 1 plus blah blah blah, but beta n ln alpha n, where the beta n's and alpha n's are complex algebraic numbers, with all the alpha n's being non-zero. Complex algebraic numbers, this means that they are complex numbers which are the roots of polynomials with rational coefficients. Technically here, the subject, even though the natural logarithm is multi-valued, such expressions we will allow ourselves to consider any possible value that they can attain. So of particular interest is the case where we restrict the alpha n's and beta n's to a particular number field, with the simplest case being the one in which all of the beta n's and alpha n's are rational numbers. The classical problem of linear forms of logarithms is finding a lower bound for their ordinary absolute values. In the n equals 2 case, letting the alphas be 2 in q and letting the betas be integers m and negative n, suppose we have an inequality of the following form. It's m times ln2 minus n times lnq is greater than or equal to a over m to the power of b for some constants, positive real constants a and b. If q to the m is greater than q to the n, we get that this has to be positive here, and so this lower bound becomes as follows. If we apply exp, we get 2 to the n, 2 to the m is greater than or equal to q to the n, e to the a over m to the b, and so then taking this difference, we replace 2 to the m with the lower bound, factor out the qn's, and then use the elementary inequality e to the x minus 1 is greater than or equal to x. Applying a similar argument in the case where 2 to the m is smaller than q to the n gives us the following lower bound. Now, so in other words, the lower bound on this linear form of logarithms tells us that we have a lower bound on the difference between a power of q and a power of 2. In particular, it's proportional to q to the m over n to the b. In this way, lower bounds of linear forms of logarithms can be converted into lower bounds on the Archimedean distance between two exponentials. And both of these lower bounds happen to be true, with this thing here being a special case of Baker's theorem, which gives lower bounds to the absolute values of arbitrary linear forms of logarithms of algebraic numbers. Alan Baker died a couple years back. He won the Fields Medal for this result because he could then use it to find bounds on solutions of various complicated Diophantine equations. The problem is, this element estimate, while very nice, is not sufficient to prove Collatz. As Tao explains in his blog post, the Collatz Conjecture, Littlewood-Offord theory, and powers of 2 and 3, quote, any proposed proof of the Collatz conjecture must either use transcendence theory or introduce new techniques that are powerful enough to create exponential separation between powers of 2 and 3. While chi-q and the correspondence principle do not yet furnish such new techniques, they do help us glimpse what kinds of advancements in transcendental number theory might be needed in order to resolve the weak Collatz conjecture. Recall, the weak Collatz conjecture is the assertion that 1, 2, and 4 are the only positive integer periodic points. For T3, this means 1 and 2 are the only positive integer periodic points. To that end, it's very useful to consider the following table, and here we're going to recall that chi-q of b2 of n is this rational number. So let's take a good look at this thing. What this shows is here we have n, here's the value that chi-q of n takes, here's the value that chi-q takes at b2 of n, and then here's this column for q equals 3, q equals 5, and q equals 7. By the correspondence principle, we know that a non-zero integer that is a periodic point of tq is, every such integer is in this list, and an integer is a periodic point if and only if it appears in this list. Now, the reason why I do this in Q is not just to make it easier to analyze, but to make a point that we'll see in a moment. So, but just notice that we get here, this is technically the fixed point at 0. For chi3, this is T3, T3 fixes, has negative 1 as a periodic point, 1, negative 1, negative 7, negative 5, negative 1, 1 again, negative 1. For the 5x shortened 5x plus 1 map, we get -1, -1. The reason why these occur is because the number of binary digits of n is related to the length of the cycle. So if you want to make sure that this thing will produce periodic points, you have to have n has at least as many digits as the number of terms in the cycle in order for them to appear. So we'll look at this, and now we're going to take a greater detail and look at this particular thing. So as I said, all those periodic points that appear, examining this thing, we see a few patterns. So one is that B2 of 2 to the n minus 1 is always going to be sent by chi-q to 1 over 2 minus q. More significantly, as n it varies over the positive integers, chi3 of B2 of n appears to be more likely to be positive than negative, whereas the opposite appears to be true for q greater than or equal to 5. Here, this is positive more times, but here there's so many more negatives because q is now bigger than or equal to 5. Of special interest is the cases when n equals 2 and n equals 10. There we get the following. Chi-q of B2 of 2 is 1 over 4 minus q, and chi-q of B2 of 10 is another rational function of q, but which simplifies to 1 over 4 minus q, so the results are the same. A moment of thought shows why this is the case. If we look in base 2, the digit sequences of 2 and 10 are 0, 1 and 0, 1, 0, 1. Again, recall, we write the digits left to right in order of increasing powers of the base. So, letting j be 0, 1, we have that 2 twiddles j, and 10 twiddles the concatenation of j with itself. B2, meanwhile, acts like a projection, as we saw, it's idempotent, and with B2 of the concatenation of k copies of j, that's the same thing as applying B2 to j in itself. So this then leads to the following definition. Fix an integer b greater than or equal to 2. I then define a relation squiggle on the set of strings in base b, finite strings, and this relation is easily shown to be an equivalence relation, and it's the following. I squiggles j if and only if there are positive integers such that if we concatenate I m times and j n times, we get the same thing. I call the equivalence classes of the finite strings under squiggle the root classes, and then I define the map root b from strings to the set of root classes by the following rule, that root b of j is the shortest string which has the same, that went way too far. And where was, yes, we're going to define the root b of j, it's the shortest string which has the same root class as j. I then say j is b irreducible whenever j is its own root, and say that b is reducible otherwise. By our identification of strings with integers, I extend this terminology to non-negative integers. Specifically, given a integer n greater than or equal to 0, root b of n is the integer represented by the string root b of j, where j is the shortest base b string representing n. I then say n is b irreducible if it's its own b root, and say it's b reducible otherwise. Two integers belong to the same b adic root class if their shortest representative strings belong to the same root class, and so I write n squiggle m with a little subscript b whenever this occurs, and then n0 modulo this equivalence is the set of b adic root classes. With these definitions, for each n, let's consider the following formal polynomials. dn equals this, and big N, little n of x equals this. Just note, this is what happens when we write this. Oh, this is wrong. This should be this should be a dn down here, so I might screw that up. So anyhow, what happens if you clear denominators on the numerator and denominator of this thing is you get this rational function. Here we're going to treat q as an indeterminate, x. And we then define, for any bold j, we define r bold j as n bold j of x over d bold j of x, where bold j is the string representing n. So it is easy to show that this formal polynomial does not depend on n, but rather on n's two-adic root, or binary root. So let m and n be positive integers. Then if m and n belong to the same two-adic root class, the Rm and Rn are the same rational function. And the proof is immediate because it's due to the fact that B2 is a projection. I'm confident that the converse of this problem is true, but I've yet to prove it. So looking back at our table and this phenomenon that we saw here where this expression simplified, we note that there are going to be two ways in which Rn of q can evaluate to an integer. The first is that if we look just in this column, we get some kind of division where the denominator as a polynomial in q divides the numerator as a polynomial in q. However, if you look, and this is very easy to show, the numerator always has degree at most one less than the degree of the denominator. So this divisibility can never occur. As a result, the only way that we get the other alternative is that rather than the divisibility occurring in this formal rational function, it occurs after we evaluate at a particular value of q. So as an example, here when we evaluate things at q, in this case, when q is 3, we get 1 over 1. When q is 5, we get 1 over negative 1. But now notice something. Here we get negative 7, but when we plug in 3, 8 minus 3 squared is 8 minus 9, which is negative 1. Here when I plug in 3, I get 8 minus 3 squared, which is 9. 8, which is negative 1 again, and the same thing. And likewise here. Here I get 16 minus 3 squared, which is 16 minus 9, which is 7. But the numerator here is also 7. Likewise here, if I plug in 5, I get 9 over 16 minus 25, which is negative 9. Whereas here, if I plug in 5, I get negative 1. So what we see is this following pattern. What we see is that in all the cases in our table where chi q of b2 of n evaluated to an integer, the reason this happened in our table was because the denominator of the left column here, this column here, when evaluated at q, was going to be a trivial divisor of the numerator. That is to say, dq n of q was either 1, negative 1, or the numerator, or negative of the numerator. So this makes us wonder the following. For any positive odd integer q, and any two irreducible n, meaning that when you write out the sequence of n's two-adic digits, there's no way to write that as being generated by a strictly smaller sequence, the following are equivalent. dn of q divides nn of q, and dn of q is either 1 or negative 1. In other words, what my conjecture is that when I evaluate q to be any odd prime number, if the denominator divides the numerator, it's only because the denominator is, when n is two irreducible, it's only because the denominator is a trivial divisor. So my claim is that when we simplify by evaluating a q, we never end up with only with being a non-trivial divisor, or with there being, say, a divisor here and a divisor there that partially cancels out, but there's still something left in the denominator. This conjecture seems kind of harmless, right? It's not. Thanks to Mihailescu's resolution of the Collatz conjecture in the mid-2000s, we can actually show that this is equivalent to the weak Collatz conjecture in the case where q is 3. First, let's state Mihailescu's result. It's the proof of Collatz Conjecture, which is that the only choice of positive integers x and y and integers m and n which are greater than or equal to 2, for which x to the m minus y to the n is equal to 1, is the case when x is 3, y is 2, m is 2, and n is 3. So now we have a corollary of Mihalyevsky's result. Fixing q equals 3, this conjecture is equivalent to weak Collatz. So first, let's suppose our this denominator conjecture, I'll call it, is true for q equals 3. Now, what that means is for any n such that dn of 3 divides nn of 3, it must be that dn of 3 is either 1 or negative 1, and n has to be 2 irreducible. So suppose we have x be a positive odd integer, which is a periodic point. Then by the correspondence principle for periodic points, there's going to be some positive integer n such that chi3 b2 of n is x. Without loss of generality, we can suppose n is 2 irreducible. If not, we'll replace n by its 2-adic root, and then we just use the fact that b2 sends the root of a number, 2-adic root of a number, to the same thing as the number itself. Then, by our assumption of the truth of the denominator conjecture, if because this is an integer, dn3 must divide nn3, which forces dn3 to be 1. So dn3 is going to be 2 lambda 2 of n minus 3 to the number of 1s of n. And this being equal to 1, or 1, technically I should also say negative 1. So in this case, if for both this and for the negative case, if lambda 2 of n and negative 1 of n are greater than or equal to 1, we can apply Mihalyevsky's theorem to conclude that this equality is impossible. So either lambda 2 of n must be less than or equal to 1, or the number of 1s of n must be less than or equal to 1. And if lambda 2 of n is less than or equal to 1, then we know that n is either 1 or 2, and so checking our table, we saw that, checking our table, we see that n can have at most one digit, and since n is greater than 1, it has at least one digit, which forces n to have a single 1, which forces n to be of the form 2 to the k for some integer greater than or equal to 0, and so we just run through everything, and then we get this, which then forces k to equal 1, thus n equals 2 to the first, which is 2, and so x equals 1. This so conjecture 11 for q equals 3 implies weak Collatz. Conversely, suppose that weak Collatz is true. Then the only positive integer value taken by chi3 of b2 of n is 1. So here's our claim, is if n is greater than or equal to 1 and makes b3 of b2 of n equal to 1, then n has a 2-adic root of 2. Let n be as given. Following the proof of the periodic point correspondence principle, note that the string j representing n generates the motions of 1's trajectory under T3. Specifically, the digits of j will encode the motions that 1 will follow under as it goes around its cycle k times for some positive integer k. This cycle is a sequence 1, 2, followed by 2 to 1, which corresponds to the string 0, 1. So j must be a concatenation of this string, and since j is 0, 1 represents the integer 2, this shows that j, which represents n, is in the same root class as 2, which forces n to be in the same root class as 2, which means that root 2 of n is equal to 2. So by this claim and the assumed truth of the weak class, we have that 2 is the only 2 irreducible integer for which n of 3 over dn of 3 is in z. Since d2 of 3 is 1, we then have that as n varies over the set of 2 irreducible numbers, nn of 3 over dn of 3 is an integer if and only if dn of 3 divides nn of 3, if and only if dn of 3 equals 1, which is precisely the denominator conjecture for q equals 3. So the two conjectures are equivalent. In light of this, we see that in order to prove the weak Collatz conjecture, we need to show that as n varies over the 2 irreducible positive integers, the number dn3 is never a proper divisor of nn of 3. While it is not inconceivable that Archimedean estimates of nn of 3 and dn of 3, such as the Baker's style results, might be of use in such an endeavor, it seems obvious to me that the road forward must involve getting control over the L-adic absolute values of this number and that number for an arbitrary prime L. That is, rather than being an additive question, or at least a purely additive question, the number theory at work in the weak Collatz conjecture is, at least in part, multiplicative. It's also worth noting that even before we've opened the box of PQ-adic Fourier analysis, we can see there's an interplay between treating Q as a formal indeterminate and treating it as a number. Though scheme theory seems to me a turgid morass of terrifying abstractions, even I know enough to recognize that schemes involve thinking of elements of rings as functions of prime ideals by way of the send the element of the ring to its equivalence class modulo a given prime ideal map, which is exactly what we were doing when we replaced big X with Q for our rational function in its numerator and denominator. This makes me wonder if we might be able to view chi-q as a scheme-valued function of a two-adic integer variable. Possibly we might have to first restrict chi-q to the rational two-adic integers. Unfortunately, I suck at commutative algebra due to horrible experiences in graduate school. I basically have algebra/abstraction-related PTSD, so I could really, really use some help figuring this stuff out. Finally, we have the airing of the grievances. I've never seen Seinfeld, but I know about Festivus, and I think what you do during the Festivus holiday is air grievances. So if that's the case, then good. So, with all due respect to my PhD advisors, Nikolai Haydn and Sheldon Kamiani, who were and are wonderful in every way, unfortunately, I had a pretty shitty graduate school experience. It wasn't my advisor's fault, it was my fault. Due to being improperly informed as an undergraduate, I only did the baby versions of group theory and ring theory. If you go to UCLA, this means I did the ordinary course sequence rather than the honors course sequences. No one told me the honors sequence was the one that the serious math majors ought to take. I did not see tensors, tensor products, Galois theory, differential forms, or algebraic number theory until graduate school. I did not do a course in algebraic number theory. I just listened to Sheldon lecture me about the topic. A very nice lecture, no homework. I took notes, but basically I know nothing. I never touched algebraic geometry, either classical or modern. I wasted my time taking undergraduate analysis courses at UCLA when I was there. It's when I should have been taking graduate courses. I only took 2 quarters of UCLA's complex analysis graduate course. I was and continue to be severely limiting my own options because I'm not comfortable with living away from my family home in Los Angeles. I'm autistic and I have genuine and obsessive compulsive, and I have genuine worries that I will not be able to survive as an independent adult, particularly once my parents kick the bucket. I could say more about this, but I don't want to be getting myself in too bad of a mood, so I'll leave it aside. I only attended a single conference as a graduate student, though it could be argued that the number of conferences I attended is actually 0. You see, the conference I attended was held the day after I graduated with my PhD. It was a special section of the Western Conference of the American Mathematical Society, done over Zoom, and it focused on research being done by graduate students. Other than the other presenters and the event's hosts, no one came. Anyhow, I have my grievances. So, it could also be argued that I did not one, but 2, hello Reddit, goodbye Reddit, I did not one, but 2 dissertations. When I was first bitten by the Collatz bug in March of 2017, I was approaching the problem using the reformulation of the conjecture in terms of functional equations for holomorphic functions. I independently rediscovered this reformulation, originally found by Meinardus and Berg in the late 1990s, early 2000s. The idea was that solving Collatz is equivalent to characterizing the fixed point of the following operator on the space of holomorphic functions on the open unit disk. What we do is we take a power series, convert with radius convergence at least 1, and then we apply the shortened Collatz map to the subscript of the coefficients. I called this a permutation operator. My Dreamcatchers for Hydra Maps paper on arXiv contains the resulting findings. It was a cute idea, but ultimately it went nowhere, or rather I wasn't clever enough to figure out how to make it go somewhere. Nikolai Haydn at USC did me the favor of looking through my work and finding the inevitable errors, at least early on. At this time, 2017, 2018, I began pestering Jeffrey Ligarius over at the University of Michigan. He was nice enough to read my hopelessly flawed write-up and showed me Meinardus and Berg's work to let me know I was treading on old ground. In the autumn of 2018, when I first met Sheldon at the USC, taking that algebraic number theory seminar, I just basically gave up. Along with Nikolai, Sheldon would go on to become my advisor, and I got Nikolai's help in writing a solicited letter. Nikolai wrote to the professors I was messaging in advance, telling them that I was writing to them, and we sent letters to mathematical analysts, especially of a number theoretic flavor, up and down the California coast, explaining what I'd been doing and asking if they'd be interested in taking me on as an off-site graduate student. The deeper I got into my work, the further away I got from USC's mathematical research foci. USC's analysis department, for example, is almost entirely PDEs and probability theory. So no harmonic analysis, no analytic number theory, no non-Archimedean analysis, no complex analysis, nope, none of those things. That's why I was hoping to get in touch with a professor from another university who might be better suited to my interests. Yes, I was stubborn. Sheldon had offered me problems involving behaviors of elliptic curves under quadratic or cubic extensions, but I didn't want to do that. None of the people we messaged replied. One of the people we messaged was UCLA's own William Duke, who did reply, but only after I called him and asked him in person, and asked him directly. He told me no, obviously. Ironically, I had an encounter with Professor Duke once before as an undergraduate at UCLA when I was attending a review session he was holding on linear algebra for students who wanted to take the basic qualifying exam normally given to graduate students. Had I passed the exam, I might have been able to graduate from UCLA with honors in mathematics, but I did not. Anyhow, at this review session, after I made a question comment about what he was talking about, I don't remember what it was exactly, maybe something to do with eigenvalues, he pointed at me and said, "You're going to prove something interesting someday," due to the unusual way I've been thinking about the content. I'd like to think that I fulfilled his prophecy. I got in touch with Jeffrey again when I discovered the things that I've been showing to you. In late 2021, he said he would get back to me. He never did. Maybe he forgot. Maybe not. Anyhow, Michigan people, or Jeffrey people, or both, please pester him for me. I am currently in touch with one of Jeffrey's colleagues, the lovely Alex Kantorovich. Alex is friendly enough, though he's told me he's sworn off working with other people on Collatz, so yeah, that's less than ideal. Back in 2022, I sent an email to Peter Schulze, because I was told by someone on an analysis Discord server that my frames method seemed similar to what Schulze and Clausen have been doing with their condensed mathematics program. Amazingly, Schulze responded within a day or two and told me that no, there was no similarity, and that he didn't find my findings as interesting as I did. As a result, I am now 100% on Team Schulze. Take that, Mochizuki fanboys. I cannot sing the man's praises loud enough. I sent him an email, and he responded. It's only an epsilon of time, and it makes all the difference in the world. Every once in a while, I get messages from the lady asking me to look into their Collatz stuff. I am more than happy to oblige them. I ended up, so I just didn't continue talking about this stuff. So, let's see, what else? And then, of course, there was the message I sent to Kiel back on the 14th. I got no response from there. I've sent messages to people who generalized Terry's work on using his methods for hydromaps with an arbitrary number of branches. I told them about what I was doing. They told me politely to shut up and just post something to archive, which I did, and I told them about it, and again, no response. So let's see here. I would like if on that maths Discord server that Anthony Vasutoro is maintaining, I've been in contact with some graduate students at UCLA who advised me that you need to go talk to X person in order to give a talk at the university. Sent them messages. No reply. I sent messages to the people at the online analysis research seminar, a lovely thing. They did not reply. I've sent messages to one person who did reply is Professor Andrei Krenikov of the Linnaeus University in Sweden, and he helped me get my first two papers published, so I'm internally indebted to him. Oh, also, ACM Van Ruige, one of W.M. Chikoff's colleagues, I cannot determine whether or not he is dead. He is taught at the Catholic University of the Netherlands. They call it something different now, but he has a what's that thing? That Research Direct. He has a Research Direct account, and I sent him a message, no response. I don't know if it's because he's dead or just very retired. If anyone of a Dutch persuasion or a Catholic University of the Netherlands persuasion, although they've named it, if any of you are up there who knows if or not he's alive, please ask or let him to see this. I'm curious to see what he thinks about this. So also, again, Pester Jeffrey, I'd like to get his attention. And Professor Duke does L functions and modular forms and stuff. So he might be interested in the next episode, which we're going to see how to rewrite the weak Collatz conjecture as a contour integral. We'll be doing that, which is very fun. He might be interested in that. But just like let him know that I'm still here. Anyone else I think to mention? Yes. That analysis server, they believe it's called the analyst's lair. Within like maybe a week of joining, I was summarily kicked out and just banned from it because the moderators believed that my PQ adic analysis was just crankery, and I've tried messaging multiple people about this, including the people that gave me the recommendation, and they've completely ghosted me, ignoring me. I'm incredibly sore about that. I also got banned from the big mathematics Discord forum because I was talking about an issue of my story, just discussing with some people. I was discussing the idea of a succubus being that could steal people's gender, and they didn't like the fact that the talk was getting sexual. I apologized for doing it and stopped it immediately, but I got banned summarily, no chance of appeal, no nothing, and unfortunately the mods on that server are basically dictators, and so I have no chance of appeal, and I honestly, I cried about that. I would not have gotten my dissertation finished without the help of the people of that server. They helped me format the thing. They made me aware of the Galois conjugate issue, which I've since done a lot of exploration in, and it just really hurts getting cut off from that community, especially because, as I said, I had a shitty graduate school experience, and so basically had no mathematical interactions outside of the class at all. And it wasn't until early 2022 when I was working on my dissertation that I first joined the big mathematics Discord and the analyst lair. Although again, I joined the big mathematics Discord after I was kicked out of the analyst lair, and so it was amazing being able to be part of those communities. I have since migrated over to the to Vasitoro's modern number theory server, which has been endlessly helpful. They've been helping me bone up on my algebraic number theory Galois stuff. They've been putting up with my stupidness. One of the person even finally explained to me how to multiply two cubes, as in like two 3x3x3 arrays. I'd always wanted to do that because for me, a tensor is just an n-dimensional array of numbers, and I've always wanted to know how to multiply two cubes together, because when you take two matrices, two squares, you take the row and then you dot it with the column and you do that. And I learned that when you take the product of two cubes, the result is a hypercube, a four-dimensional cube, and I found that really interesting. Anyhow, the Vasitoro Discord is it's almost entirely algebraic geometers, because the Discord emerged out of Vasitoro's wonderful series of videos about Fermat's last theorem, and as a deeply classical analyst, I feel like a fish out of water, and it would be really great if I could be in a community of people who can talk about things other than schemes and sheaves, but I can't, and I'm not, and it hurts. Okay, I'll just get personal about this. So I do not have closure from my PhD dissertation. At the moment, I feel like it was a waste of time. My advisors, again, they're great, but they don't understand what I'm doing. I barely understand what I'm doing. Sheldon does arithmetic geometry. He worked with Maser and Wiles. Works on elliptic curves, their torsion groups. Nikolai does ergodic theory. with dynamical systems and in invariant measures and that stuff. And so none of them would know anything about the non-Archimedean analysis or harmonic analysis or stuff that I've been doing. And I've just been waiting for someone to come and sit down and to talk with me about my thesis at the level that I'm talking about it. And because as an undergraduate, I did a history thesis. I was also a history major. I would have been a biology major or a physics major if UCLA hadn't counted my AP courses against me, so I didn't have enough units. But I did a senior thesis on U.S. economic history in the 19th century under the supervision of Mary Yeager, who again is wonderful. I also, in my first year, did a minor thesis on Hagen from the Nibelungenlied with Professor Joseph Nage, and that was a wonderful experience. He is a professor of Celtic literature. And so I know what it's like to be able to interact with academics at their level, and it's just a joy for me. I have never gotten that experience from mathematics, which is part of the reason why I have this gaping hole in my heart when it comes to my dissertation, because there's no one I can talk to about it. Part of the reason why I want to get in touch with Tao is because he's a very smart person. He knows basically everything. And I feel like I could talk to him about the things that I'm doing. And rather than getting rather than Sheldon getting worried about his inability to do computations, or Nikolai wondering, well, how does the hardy little Tauberian theorem work? I could be able to talk and not have to worry about that. And just for me, and I said this in my the letter that I wrote to for part of my application, my statement of purpose to graduate school, is that Paul Erdős, when he had a very unique way with language, and when people died, he would say that they left, but he would say that a person died. He would say a person died when they stopped doing mathematics. For me, whether it's mathematics, writing, anything I do, the ultimate purpose of it is so that I can engage with it in other people. I don't really care for hanging out. I'm not interested in sports. I don't go to bars. I'm asexual, so all of that stuff is just out the window. And for me, working in an academic context is where I get my social interactions. I like doing math and science and history and unraveling the mystery with other people. And so it's been really soul-crushing to be so absolutely, utterly alone. Yes, every PhD earner is going to focus on a tiny bit of information, but at least they can connect to something else, and they can talk to other people who are doing what they're doing and can find a sense of camaraderie. I've never gotten that. And so all the people that I mentioned, Jeffrey, Terry, Bill Duke, even Schulzer, although what he's doing is so impossibly complicated, I'll have no hope of understanding it. Even more than a collaborator or someone to help actually flesh the stuff out and put out some textbooks, I just want somebody I can talk to, just casually. When Jeffrey Ligarius wrote me messages, he did not use complete sentences. He used that journal referee speak where there's spaces and it's weird. I'm the kind of person, when I write an email, I write long paragraph sentences, very detailed, very in depth, and I just want to be able to interact with someone. My Discord server, again, it's open. Anyone's willing to come, I'd be happy to explain things. I've done it many times before. As I said before, I'm in desperate need of algebraic geometers, because the stuff we saw with treating this as a ring of functions, rational functions, and then we consider quotients, modulos, these certain prime ideals to evaluate them. I'd love to be able to figure that out and how to get that in the commutative algebra setting. And then there's the possibility of that curve, of CQ, that curve that I mentioned here. Maybe we can do étale cohomology or étale fundamental groups of this thing to figure out where its self-intersections are. Again, I don't know. I freeze and panic whenever I see the word morphism. I can't handle the abstraction, and it's very difficult for me. I'd very much like someone else to work with. I am not very smart. I Yeah, I'm amazed that as many people are interested in this as it is. I just think it's neat and want to share it off with people, not because I want to brag or anything, but for me, mathematics and really everything else, it's about sharing. If we had a cure to cancer, but it was written in a language no one understood, we might as well not have a cure at all. All this knowledge that I have and all the knowledge any of us have, its value stops at our ability to, it's limited by our ability to share it and convey it with others. And so without those connections to have, we have nothing. So yeah, those are my grievances. And I have a Patreon. I'll probably, it's for my story. I made a whopping total of $18 from one person for 2 months in the middle of this year. I'll set up a separate tier listings for people who want to pay things to give me money to keep doing my research, but I'll include the links below to that. And if they're not currently here, I'll put them there. And so, yeah, it sucks. It's sad. I have been beating myself up over the past few days because I feel like I haven't been making enough progress on my book, even the fiction, even though I've already written over 1 million words this year. This is first draft, second draft, outlines, everything. It's not fun. I don't like being intellectually isolated, and I would like to be able to send emails to professors and at least get a response saying, just no thank you, I'm not interested, rather than just the void of silence that I currently have. So yeah, pester people, everything, and that's my sad bullshit. I'll see you all next time for episode 4, when we will rewrite the weak Collatz conjecture as a contour integral. Bye for now.